In this lecture, we will get a closure on the introduction of first law of thermodynamics. In a set of previous lectures, what we did was introduce work in terms of generalized intensive forces and generalized extensive displacement. And we also introduced heat. So it is a form of energy transfer from region of high temperature to region of low temperature. And it is, there are three forms: conduction, convection, and radiation. We also elaborated on reversible transformation. All this has been done. Why did we do it? Okay, so all these come together in the form of first law of thermodynamics. So essentially, the first law of thermodynamics is about generalizing the work energy theorem and conservation of energy beyond mechanics. Okay, so if you want to go beyond mechanics, we have to introduce one particular term. Okay, for example, in mechanics, when we thought about delta E, okay, change in energy, we are more thinking about changes in kinetic energy and changes in potential energy. But if you want to generalize this to energy changes to thermodynamics, we have to introduce delta U. Okay, so this is change in internal energy. So all these things put together, the simplest mathematical statement of first law of thermodynamics is this: change in internal energy is equal to heat and work exchange. Q, the heat exchange, minus W. So there are certain fairly intuitive sign conventions we adopt to frame the first law of thermodynamics. So we say if the work is done by the system, we assign a positive sign to work. Okay, so what does it do? Actually, if this is a positive number, when work is done by the system, delta U will decrease. Okay, so if work is done on the system, that'll be negative of negative will be a positive number. So the internal energy will increase. Okay, so you need not really memorize the sign convention. If you have this form, the sign convention is sort of intuitive. Same thing with heat also, right? If heat transfer is to the system, that will increase the internal energy. So we assign a positive number. If heat transfer is from the system, you assign a negative number. Okay, so you can have the opposite sign convention if delta U is stated as Q plus W. Okay, so these are nothing very conceptual. So just if you have this form of the first law, instead of Q plus W, then corresponding to this form of first law, these are the sign conventions. So there are many forms of first law, and another form that was originally introduced, okay, the early days of first law of thermodynamics, is to consider a cyclic process. So what do you mean by cyclic process? This is often seen in the analysis of many systems in thermodynamics. We will again use such cyclic process to analyze the second law of thermodynamics. But here I'm introducing the meaning of a cyclic process. You start at one point in the thermodynamic state diagram. You do a set of changes. For example, here P and specific volume, it's plotted in P and specific volume state space. So you do a set of changes such that you come back to the original point. Okay, so that's called a cyclic process. You can do this all the time. So what would be nice is if while doing a cyclic process, you can get work out of it. Okay, so in a way that you can get something out of nothing. All right, so what the first law states is that a perpetual motion machine is impossible. So what does a machine what we would like to do with the perpetual motion machine is that under a cyclic process, you should be able to get net work, all right? That's not possible. So because of the statement of the first law of thermodynamics, this is indicative of a cyclic integral. So you go around this entire loop. Delta U is 0, because of which W is equal to Q is equal to 0. Okay, so you can never get work out of a cyclic process. Okay. So there are a variety in work and heat interactions. For example, this the work done by a battery. For example, the current goes through a ohmic resistor. It eventually gets transferred as heat and to changes in um, energy, right? So this is an adiabatic wall. There is no heat transfer via the wall. All the work transfer is via this current wires. Okay, so you can imagine again shaft work, because Q is 0, all the work done goes towards increasing delta E by 5 kilojoules. That's the work that is done here also. Okay, there is no change in kinetic energy of the center of mass, potential energy of the center of mass. So this change is the change in internal energy, and Q is equal to 0. Same thing here. Shaft work is 8 kilojoules, Q is 0. There's no change in potential energy or kinetic energy of the center of mass. So delta E is 8 kilojoules, and it shows up as increase in internal energy. In this case, there is a liquid that's being heated. So the energy that is supplied is 15 kilojoules, because this boundary can allow heat to come in, and some heat also gets out, because this is at a higher temperature compared to the environment. 15 minus 3 is the work exchange that shows up as increase in internal energy. Okay, so this is via rigid wall, the enclosed and rigid wall. So there is no PV work and there is no other forms of work interaction. Here there is PV work and there is no other form of work or heat interaction. So the PV work imposed on the system shows up as change in internal energy. So these are all fairly simple implementation of first law of thermodynamics, but it's good to get used to the sign conventions and so on, right? So here is slightly more complex in the sense that both work and heat exchange occurring simultaneously. There's a shaft work as well as heat transfer. So just bookkeeping, simple bookkeeping will tell you how much is the increase in internal energy. Another jargon which you need to be aware of, we'll be using this often, is what is referred to as exact and inexact differentials. Okay, so this is just an introduction to this terminology. We'll use this again when we introduce the second law of thermodynamics. Okay, so when we say something is an exact differential, this is what we mean. Here, what are we plotting? So we have plotting P is in the y-axis, specific volume is in the x-axis. So when there is a state 1 and there is a state 2. Okay, so in state 1, specific volume is 2 meter cubed and specific volume in state 2 is 5 meter cubed. So when you say what is an exact differential, okay, so it doesn't really depend upon the way you go from one state to another. Okay, so the changes in specific volume is just a property of something in state 2 minus something in state 1. Okay, so specific volume change from 1 to 2 is, you can express it as this property, property that is only dependent upon position 2, and another the other limit on the other end. Okay, you have something that depends only on state 1. Okay, so that's what you mean when exact differential. However, when you're thinking about heat and work exchange, when you go from position 1 to position 2, there are variety of ways you can go from position 1 to position 2, and all this thing, the way you go from 1 to 2 would determine how much of work and heat exchange has occurred, right? So even though delta change in specific volume in process A and process B is the same. Okay, so it is 3 meter cube. The work exchange can be different. Okay, because work is an integral of PdV. So if you look at process B, the work exchange is more compared to process A. Okay, so if something depends upon the way, the path, right? That's called a path function, and such an integral is called an inexact differential. Okay, so that is the simplest introduction, and we will see the utility of these terminologies later with respect to second law of thermodynamics. So when something is an inexact differential, we use a slightly different notation. So here we are referring to this as delta V, but here this is not delta W, indicating that this is not an exact differential. So there are few other forms of first law of thermodynamics. So sometimes in engineering system, we are interested in time rate of change in energy, right? So for this, we have to bookkeep the rate at which the heat transfer occurs, the rate at which work transfer occurs. Okay, so this form of first law is also used. And in some cases, we like to mention the first law in terms of quantities normalized by mass, right? So all these term energy is per unit mass. Okay, so this is another form of first law. So these are all minor extensions, but very useful extension when you are looking at engineering system. In many engineering systems, the system that is being analyzed is not a closed system. So there is some flow processes. There are three kinds of flow. There can be mass flow. So they're no longer a closed system. There can be mass in and mass out of the system. There can also be work and heat flow between the system and the environment. Okay, so you do a grand bookkeeping, taking into all three processes, and this form of flow system will be analyzed in the next few lectures. So there can be energy flow just due to mass input and mass exit of mass. That is this term. We will get to the quantitative definition, how to specify these terms in the next few lectures. And these are the other two terms. These two terms you've seen in the expression for thermodynamic first law in a closed system. These two are the same as what you have in the first law expression for a closed system, but these are the two new terms. How do you express E, energy of the incoming mass, and energy of the exiting mass? We'll see the specific mathematical expression in the next couple of lectures. So this is another form of first law that will be used in analysis of engineering system. So with this, we end the introduction of first law of thermodynamics. And what we will see in the next couple of lectures is trying to implement first law of thermodynamics in variety of processes. We look at, let's say, isobaric process, isothermal process, adiabatic process, and we look at the expressions that come out of it. These are some extremes. Okay, so most of the real process which you see in engineering system might not fall into one of these extremes. Okay, but however, looking at these extremes gives you certain insight into what happens in these extremes, and the real process is somewhere in between. Okay, so that is the trajectory we will take for the next couple of lectures. Thank you.